All right, so today what we are doing is actually hypothesis testing by itself. Now, hypothesis testing is a very big topic. So let's look at a bit of revision because this is supposed to be in a tutorial session. So what are the steps of hypothesis testing? Anybody remembers? What's the first step of hypothesis testing inside your lecture notes? Go and look at your lecture notes. What's the first step? Yep, what's the first step? So we just read out. First step of hypothesis testing. Okay, what's the first step? Okay, actually the first step of hypothesis testing, you can call it almost step 0. Okay, first you need to define what is your research question that you want to ask. This research question is also sometimes known as your research hypothesis. Okay, so from the research hypothesis, you define what is the statistical hypothesis. So statistical hypothesis always comes in pair. You have your null hypothesis, which we define, the symbol is H0, and the alternate hypothesis. Alternate or alternative hypothesis, which is H1. Some books, they write it as HA. Okay, depending. So statistical hypothesis, you need two. All right, and very important, your null hypothesis is usually the hypothesis of no difference. The research hypothesis that you actually try to find out tends to be the alternate hypothesis. Okay. So let's say, for example, let's just use an example. Let's say the research hypothesis you want to find out, does chemical A increase cell survival? That's your experimental hypothesis, your research hypothesis. Okay, so in this case, the null hypothesis is that chemical A does not increase cell survival. Okay, so that's a hypothesis of no difference. Mathematically, you write down as, let's say, the cell survival, the average cell survival for control equals the average cell survival for treatment, or in this case, we chemical A. Okay, then your alternate hypothesis in this case becomes chemical A affects cell survival. Okay, and then you write as control is not equals to when you add chemical A. So this is although we say increase, right? But quite often we put it as a two-tail test. Okay, so we don't bother about one tail, two tail for now. Okay, when we come to Thursday, do you have practical on Thursday again? Anyone? Okay, so half of you will be here. Okay, so when we come to Thursday, then we look a bit closer at one tail or two tail test. Okay, in this case, by right, it's supposed to be two tail test. Okay. If it's one tail test, then this chemical A increase cell survival. will be changed to chemical A actually affects cell survival. That's two-tailed test. That means it can be lowering cell survival or increasing cell survival. Make sense? All right. So once we have this, then the next step, which actually still part of statistical hypothesis, is to define the threshold. So defining of threshold is very important. Okay, let's say if I tell you that your test, you score 70 marks out of 100, 70%. Do you think that's good or bad? Do you think that's good or bad? 70 out of 100. Okay. You say good, you have to define what is the threshold. In this case, the threshold for your test is what is the passing mark. Okay. It's like defining the passing mark for your test. I tell you that you score 70, you have to then know first what is the passing mark. If the passing mark is 50 out of 100, then you're doing quite well. If the passing mark is 40 out of 100, you're actually doing pretty good. But if the passing mark is 70 out of 100, then you barely pass. On the other hand, your passing mark is 80 out of 100, you fail. All right? So defining a threshold is actually very important here. Okay. So there are actually two ways to define the threshold. One is to look at the alpha value. Okay. The alpha value, let's say we do a distribution. The alpha value is basically what is the area, the shaded area. So normally alpha value, unless it's is given, we put it as 0.05. Okay. So the alpha value, you actually, from alpha value, you get the opposite. Let's say this is 0.05. You put it into 2, then it will be 0.025. Okay, each part is 0.05. Then you have this thing called a critical value. The critical value is actually the point on the axis. So this is a critical value. Let's say this is a z-axis. All right. Now for your assignments, you use critical value. Let's say for your paper calculation, you use critical value. For computational calculation, you use the alpha value. Okay. The reason is your statistical table doesn't give you every single alpha value. Okay, you only use critical value for that. Okay, later we'll come to do Excel and see what happens. So after you've done that, the second step, which is you collect your data. The third step, you calculate a statistic. Okay. So this statistic can be T, can be Z, can be anything. You calculate a statistic, a number, based on the data given. Okay. So under the assumption that you actually know what test to use first. So this statistic will be on this axis, on the z-axis, t-axis, or whatever axis. Okay. Then your step 4, you do your decision. The decision only have two options. Either you fail to either you fail to reject your null hypothesis or you reject your null hypothesis. Okay. If fail to reject your null hypothesis, since you cannot reject, you accept your null hypothesis. If you reject your null hypothesis, then you accept the alternate hypothesis. Okay. If you accept your null hypothesis, stop there. Don't touch the alternate hypothesis. Any other word that you say about alternate hypothesis is going to get you wrong. Make sense? So once you touch here, right? Do not mention about your alternate hypothesis. You accept null hypothesis, you accept null hypothesis. Don't touch alternate hypothesis anymore. You mention it, you're going to get it wrong. Okay? Only when you reject null hypothesis, then you say that you accept alternate hypothesis. Okay? So how do you accept or reject? Which one to go? When do you accept now? When do you fail to reject? When do you reject? Okay. There are two criteria, depending on which one they use. Now, for fail to reject null hypothesis, it is when the statistic, which is this statistic, is more than the critical value. That means you calculate the statistic is somewhere here. Okay. Or the p-value, the probability value, which is the area, is less than the threshold. So if the statistic is here, automatically the area that is bounded after the statistic is going to be less than the threshold. Okay, since the black part is 0.025, the red part must be less than 0.025. So either or. Okay. When do you fail to reject? Sorry, fail to reject is opposite. Fail to reject, this is here. Okay, or the p-value is more than the threshold. Then the opposite is when you reject. This is when the statistic is more than the critical value or the p-value is less than the threshold. Threshold means there's an alpha value here. Okay. So once you're done with it, you have a statistical decision. Your next step and your final step is then to do your interpretation. You interpret what it means based on the question itself. Okay. So essentially, that is how we do hypothesis testing. So far, any problems? The steps itself. Okay. These steps of hypothesis testing is kind of fixed. The only changes that you make will be here. Calculate what test to use. Use what test. Okay, different type of data, you can use different type of test and see what test is suitable. But you still have to calculate the statistic, you still have to calculate, you still have to know the threshold, the alpha value, and so on. And then the interpretation is still the same. All right, so far so good. So what we are going to cover today is your one sample hypothesis testing. Okay, one sample hypothesis testing comes in this type of question. Okay, let's say that, for example, your regular others ice cream. Okay, the printed what is labeled is 1 cup equals to 60 grams. Okay. Then what you're trying to do is, let's say, what you want to do or to test is whether the average weight per cup is equals to 60 grams. Okay. So this type of question is a kind of quality control question. Will you be bothered if, or will you be upset if other ice cream say printed that every cup is 60 grams, but you calculate and you find that on average every cup is 62 grams? Will you have a problem for that? No, right? Because it's giving you 2 more grams. You only have a problem is giving you less than 60 grams. Okay, but to the company, it's going to have a problem because it's losing profit because of that. Make sense? So quality control works both ways. So in this case, here becomes your research question. Okay. So what is our hypothesis then? What is our null and alternate hypothesis? What do you think is our null and alternate hypothesis? Actually, louder again. Alternate. The other way around. The other way around. Okay. The null hypothesis is the average weight is 60 grams. Okay. The alternate hypothesis is the average weight is not 60 grams. Okay. So the very easy way to look at it is null hypothesis always use equal. Alternate hypothesis can be more than, less than, or not equals. This is a style symbol I use. Null hypothesis is always equal to something. All right. Okay. Then you do your test and so on. Now, assuming that you have your alpha is, let's say, 0.025. Let's say that your critical value for, let's say, the Z distribution is plus minus 1.96. Okay. So after you do all the experiment, you do a calculation, you get a statistic, the Z score. And you finally get the Z score, it is 2.0. Do you accept or reject the null hypothesis? If it's 2.0, do you accept or reject the null hypothesis? Accept or reject? There's only two. Reject, correct. So what you say is, since, this is in tutorial question, since the calculated Z value is more than the Z critical value of 1.96, you reject your null hypothesis. Hence, you accept the alternate hypothesis. After that, your interpretation. So this part here, this is the decision. The interpretation will be, therefore, the average weight per cup of others ice cream is not equals to 60 grams. Okay, this is the interpretation. You have to kind of explain or answer to the question. All right. So this is a kind of structure that you use. Although in tutorial, we'll care a bit more about how do you calculate this statistic. That's all. From the data itself. Okay, so that's what we have. Now then let's look at your question. Now Excel is not able to calculate your one sample hypothesis, but we can trick Excel to calculate it. So let's us use this. Let's go to our Excel. Okay, so for example, let's do the ice cream experiment again. Okay. So let's say you go outside 7-Eleven or what, you go and buy 10 cups of others ice cream. Then you scoop out everything and weigh each cup. Okay, so you have the weight. Okay, the weight of the ice cream. Okay. Or let's repeat this then. So you want to see the question whether the weight is more than 60 grams or not. Okay, so let's say you have the weight of the ice cream, and maybe you go and buy 10 cups. Okay, so let's say you have first is 60 grams, the other one is 61 gram, then you have 60 grams again, then you have 62 grams, 62.5 grams, oops, 2.5 grams, you have 59 grams, 59.5 grams, 61 gram, oops, and the other one is 62 grams. Okay, so let's write this data out first. Do it on your computer. So how do we get Excel or trick Excel to do a one sample hypothesis for us? What you do is, in the next column, you set the null hypothesis weight. So the null hypothesis weight, we want is 60 grams, right? So you take 60, 60, out. Okay, let's say 11, we have 60.5. Okay, put the number 11 data in. So we have 10 data, 10 sample size of 10, and equals 10. All right. Then what you do is you go to your data analysis tab. And we just use t-test assuming equal variance. Okay, although I should use t-test assuming unequal variance, but we don't bother on that. Okay. Okay. There are 3 different types of t-tests. Use the second one, t-test assuming equal variance. So the range 1, you put the weight, highlight the column weight as well, the word weight, right? Column range 2 is column B. Okay. So make sure column A and column B. And what you have is you also highlighted the labels. So you click on labels, tick labels. So far, okay. Then the output range, clear output range, we want to put it on cell D, D1. Okay, put on cell D1. Everything okay already, then just click OK. So if you click OK, you will see this result. So kind of open it up. Yeah. So this is your t statistic. When you calculate on pen and paper, this is a t statistic that you have. Okay. So in this case, you have the one tail critical value, two tail critical value, the t critical value. But since ours is a two tail test, because you can see whether is it different from 60 grams. Okay. You realize that if the t statistic is less than t critical value, that is where you reject. This is where you fail to reject null hypothesis, right? Okay. So you can say that since your t is less than your t critical, okay, I cannot do the subscript here, so critical. Oops. T is less than the t critical value. You fail to reject your null hypothesis. So if you fail to reject a null hypothesis, basically you accept your null hypothesis. That's a decision. Okay. And you also realize that when t statistic is less than t critical, automatically the two tail p value, this is a p value, is more than 0.05. Okay, it is pretty much like here. Okay, so that should be. So let's say you have a distribution curve. Let's say you highlight both ends because it's a two-tailed test. You highlight both ends away. Each side gives you 0.025. So for a t, let's say this is the mean is also 0. This is the critical value. The two ends is a critical value. And the critical value is this 2.10092. So which means that at this point, this is 2.10092. This is minus 2.10092. Okay. But your t statistic is this 2.04. So 2.04, is it to the left or to lesser than this or more than this? Lesser, right? So here, at somewhere this point, this is your 2.04. And this is the t value. But this is the t critical value. Automatically, the area bounded by the t value, the blue color one, is going to be more than 0.025. The opposite end will be here. So the overall blue value is going to be more than 0.05. That's what I'm trying to say. Okay. And the two blue values, the blue region add up together, it is this 0.05594. So basically, these two blue values add up together. This is going to be 0.05594, which is more than 0.05. Therefore, you also fail to reject null hypothesis. Okay, you have to learn how to use both sides. Okay, so you can say that since the p value is more than the alpha value of 0.05, you fail to reject your null hypothesis. And because you fail to reject your null hypothesis, you accept your null hypothesis. So it's come to the same conclusion. Okay. All right. So do you know what's happening so far? Which means that you can use Excel to check all your tutorial questions. Okay. All right. So let's look at your practical 2.1. 2.1 teach you a slightly different method. So 2.1 teach you how to use this thing known as your hypothesized mean difference. Now, hypothesized mean difference is here. How do we use this value, hypothesized mean difference? Okay. Now, in order to use hypothesized mean difference, you do something quite differently. Okay, let's just take this away. So let's do the hypothesized mean difference first and follow exactly the steps. We have the data, so this is the data, but the null weight, you really have the null weight, zero weight. So you put 0 for everything. You put 0 for everything. Okay. Then you do the same. So the two data range are the same. Variable 1 range is the weight, variable 2 range is the null. But here what you want is to hypothesize the mean difference. So what you are trying to say is it more than or less than 60 grams? You put it there. This can also work. Okay, so you use the hypothesized mean difference. Then you put 60 here instead of putting the 60 on column B. So far so good. We want to compare the results, so our output range, we don't put it at D1. Now we put it at H1. So later we can compare the results. Okay, so if you're okay with it, then click OK. You realize that the T statistic will be the same. This T statistic will be the same. The critical value, in fact, these 4 values will be the same, or these 5 values will be the same. Okay. The only difference is the hypothesized mean difference is here instead of in here. Okay, that is what is given in your practical notes. But do you realize, okay, read your practical notes again. Do you realize one error that what is listed in practical notes that I did not follow here? I actually do something different from your practical. So read through the last 2.1 and up to task 1. Read the steps and see which one I did not follow. There's actually one thing I did not follow. Okay, and it's very important, that one piece of information. Okay, unequal variance is one of them. The other one? never use unequal variance. Okay, I should use unequal variance. Okay, in fact, you do unequal variance exactly what I did for 2, you get the same answer as well. Okay, as it is comparable. Yeah, it's actually on page 1. The difference is actually on page 1. Yeah. Okay. And it is very important because the difference is because I use equal variance, more likely. You look at here, ask you to create a dummy variable in the second column, which I did. The dummy variable is the null hypothesis, right? With at least 2 zeros. But they tell you how many zeros you need to add, put. Only at least 2, right? The reason why you need at least 2 is because to calculate standard deviation, you need minimum 2. But you realize here, I have the same number, same observation. Okay, so that's the difference. If I have only 2 zeros, let's say at least 2, right? I put the minimum, only 2 0. What number will change here? Out of this thing, what number will change? You realize that this number will change from 10 to 2. Right? That's the number of observations. So let's do that again and see what happens. Okay, now we put at column L. Okay. So you see, this number changes because I have only 2 values. This green number changes. Okay. And because this changes, the pool variance will change. The pool variance are no longer the same. The pool and the degrees of freedom also change, resulting in everything changes as well. Okay, that is why I have to put everything 0. I cannot just have 2. So let's look at, based on the tutorial practical slides, what happens if I use unequal variance? Will that give me a difference? Okay, the same size. Okay, you copy to this, and let's repeat this. So let's go to use unequal variance now. 1, 2, and just say the output range is no. So you use hypothesize mean first. Hypothesize is 60. The output range is in D1. Okay. So 1 is with the hypothesize mean first. Then make sure you click on labels, otherwise it doesn't work. So you get this result. Okay. If we don't use the hypothesized mean, then we have to put 60 for everything. Right, 60 for everything. Okay. But since we want to test whether if the, let's say I have only 2 values instead of all the 10 values, because say at least 2, right? Remove them and just test it out and see what happens. Put on I. Okay. So if you use unequal variance, yes, you're going to get the same result. Okay, the same result for unequal variance. But when you use equal variance, you're not going to get the same result. So please be careful with that. Okay. So all these are the minor differences in Excel that you have to be careful with it. Okay, it may sound logical to use one or the other, but it can give you different results. Okay, at the back end, the calculation is slightly different. Okay. Why we seldom bother with unequal variance? Actually, unequal variance, although it is very often we use unequal variance. Yeah, of the variances, that means the standard deviation of the two data set will be very different. For example, one is 0, the other may not be 0. Okay, so that is one case. All right. Okay, so why not you do task number 1 and see what happens for yourself? Let's say for question 10 on tutorial 5. So you do that and check your own answers. There's a spelling error here. Instead of formal distribution, it's normal distribution. Okay, check whether is your tutorial question, the tutorial answer the same as what you have. Okay, give you a few minutes to do that before we go to the next one. Okay, let me go and do this. Okay, now I'm actually typing the data for task number 2. Okay, so task, have you finished task number 1? Check whether your results correct from your tutorial questions. That's assuming that you've done your tutorials already. If you've not done your tutorials, then there's no point doing, right? All right, so so let's just do question number 2, task number 2. So I have the male and female heart rate. The question asks you to test at 5% significance. That means alpha equals to 0.05. If the mean heart rate is 70 beats per minute. So in this case, your null hypothesis is that the mean heart rate equals to 70 beats per minute. The alternate hypothesis is that the mean heart rate is not equals to 70 beats per minute. Okay, then you state all the other variables. You want the alpha. So alpha equals to 0.05. But because it's not equal to 7 beats per minute, you also need to have a two-tail test. Okay, so you have to look at two-tail test results. Okay, then let's do this. Okay. So you have the data. Okay. But now remember, we need to have the dummy data. So dummy data, since you are going to use your unequal variance, it seems to work. So let us just use this. Okay. So just put a few zeros. And what you have is the data itself. Let's go to unequal variance. Remember, you cannot use equal variance for this unless the same number of samples. So use unequal variance. So the input range, you just have the data alone. Range 2, you also have the data alone. And the hypothesized mean difference is 70 bits. Okay, you don't have the labels. And we want to put our data, our results in H1. Okay. If you are okay already, then just say okay. Okay. So what happened is it will give you this kind of error. Okay. It says that two sample assuming unequal variance, the input range must be a single row or column. So what do you think is the problem here? Why it gives you this error? Huh? Yeah, so because my data, remember, my range 1 is actually 2 columns. My range 2 is only 1 column, so I cannot do that. It basically tells me that I have to move the females, copy, put it right under here. Then I change this, instead of male female heart rate, I just change this to the overall heart rate. Okay. Then that will work. But I will need to have the data. Okay. Okay. All right. So because I don't have the labels, variable 1 and variable 2 depends on which column you highlight. So variable 1 is actually the heart rate. Variable 2 is really the dummy data. So my two-tail test, my p-value is 12.4%. So do I accept or reject null hypothesis? Do I accept or reject null hypothesis? You can use the t statistic and the critical t value to help you as well. Do I accept or reject null hypothesis? Huh? Accept, correct. Because so the conclusion is essentially, since the p-value is more than the alpha, which is 0.05, you actually fail to reject the null hypothesis, hence you accept the null hypothesis. The conclusion is, therefore, the average heart rate equals to 70 beats per minute. That means you cannot reject the null hypothesis. So you repeat the null hypothesis again. Okay. So what are some of the questions that you'll ask when you come to hypothesis testing? What are some of the common questions you ask when you come to hypothesis testing? Why do we use 5%? Alpha equals to 0.05 or 5% means that it is only when the null hypothesis has less than 5% chance of being right, then you say that null hypothesis may be wrong. If null hypothesis has more than 5% chance of being right, then you say that null hypothesis is correct. Only 5%. So in this case, when the p-value is 12%, it means that the null hypothesis have 12.4% of being correct. Therefore, you cannot say that null hypothesis is wrong, or null hypothesis is not likely to be wrong. Now, does this sound very strange to you? That null hypothesis needs to be less than 5% correct before you say the null hypothesis is wrong. It is almost like saying that your exam passing mark is 5 out of 100. Well, let me ask you in a different way. You've been studying for easily the last 11 years, so this is your 12th year already, right? Maybe for primary school and then now you don't bother kindergarten and all this. So every time when you do test or exam, what is the null hypothesis? Okay, so let me ask you, just pick either one. Is the null hypothesis that you fail or the null hypothesis is that you pass? The other way around. The null hypothesis is that you fail. That means if your marks is scored high enough that you pass, then you pass. Then you reject that you fail. To reject that you fail means that you pass. The default is actually you fail. So null hypothesis is like a default condition. It's like a condition of no difference. All right. So my next question to you is more of a conceptual question. Why we have this 5%? Why we use 5% and not other percentage? Why use 5%? Can somebody give a guess? Why in statistics we use 5%? And frankly, there's a lot of argument that we should abolish this 5% rule. Okay. Big, oh, yes, kind of extreme. Can we use more extreme than that? Can we use 1%? Can, right? The difference has to be larger. Okay. Let's say when I'm doing bioinformatics, we don't use even 1%. We use 1 times 10 to the power minus 9. 1 billionth of a chance. Okay. So there's a lot of other percentage. If you in future want work on nephrology and all this kidney research, your threshold is 10%. So it does vary a bit with the field itself. But generally, we use 5%. It seems extreme enough. Okay. So anybody know who came up with this 5%? It's a person you will learn to hate or you like him a lot. Anyway, he's dead already, so it doesn't matter. This guy is called Ronald Fisher, the one that came out with a ANOVA test. Okay, which you will learn when you come back from term break. Yeah, you learn ANOVA. Okay, Ronald Fisher is a very interesting guy. He was working on plant research. So a lot of ANOVA terms that he used is things like blocks and plots. Basically, he's talking about land. Blocks of land and plots of land. Okay. So since he came up with ANOVA, there's actually 2 stories why he came up with this 0.05 or 5%. Actually, both is in statistics books as well. So I tell you both stories, decide which one you want. The first story is this. So one day, Ronald Fisher he's one of the pioneers of statistics in 1900s, early 1900s. Okay, there's actually in early 1900s. There's 3 persons who is the top people in statistics all over the world. Ronald Fisher, Carl Pearson, which you have your Pearson correlation and your chi-square test. Okay, the other one is called Gosset. Gosset. Gosset used the pseudonym called student. That's why you have student t-test. Ronald Fisher and Carl Pearson are mortal enemies of each other. They never see eye to eye with everything else. And it's not just a private argument. They are the people who in conferences will throw things at each other. Literally throw books at each other. Okay. I can't remember which one died first, but it's always the case. Gosset, which is a student, student t-test, are friends with both of them. Okay. Now, so Ronald Fisher being one of the top people, he has to come up with a threshold. What is a good passing mark? One story is that he was thinking about this question while he's having a bath. Bathtub bath. How many of you like to have a bath? Not shower bath. The one that you have foam and rubber duckies around it. Okay. So he was thinking of this question. And the story is he was seeing that his 5 toes is sticking out of the water. So he said, okay, just why not use 5% instead? That's number 1 story. Okay. So you have more toes sticking out of water, maybe he has something else. Okay. So that's one story. The second story is he was asked in an interview after coming out of ANOVA test, which the whole world is using. And he's knighted because of that. He's a Ronald Fisher. So he was asked in an interview in a pub, what is a good threshold to use? I mean, everybody is using slightly different threshold, right, initially. So somebody has to standardize it. So he was asked by the interviewer, by reporter, what is a good threshold to use? So then Ronald Fisher came out with this argument at the point in time. Let's say there is always a possibility that I sleep tonight and I will not wake up tomorrow, right? Is there a possibility that you sleep tonight and don't wake up tomorrow? There is a possibility, right? So he was asking himself, or asking a reporter, what is the chance that if he sleeps tonight, what is the chance of something higher than that chance? That if he sleeps tonight and do not wake up tomorrow, he will not sleep tonight. It means what is the chance of death during that specific night of sleep? That he will not sleep tonight. He will rather stay awake. And give the reason is about 1 in 20 chance. So that's a 5%. His argument is anything lesser than that, he can handle. That means if the chance of dying is less than 1 in 20, 1 in 30, 1 in 40, he will just sleep. But if the chance is higher, if you put the chance higher, that means 1 in 10 chance that he will die in his sleep, then he will end up with a few days, a month of not sleeping. And by that very act, he may exhaust himself to death even. Okay. So he's asking yourself, what is the chance of dying in your sleep tonight that you will not want to sleep tonight? You take 50%, it means that half of the time you're not going to sleep. Okay. And I don't think you can function very well either. Okay, so that's the argument I made. Which story you want is up to you. Now, these are two stories I read before, and it's actually in textbooks before. Okay. All right. So we look at the glycosylated hemoglobin problem again. So look at our diabetes problem. Okay. And we want to do just question number 4. The mean waistline is below 40. So we look at the waistline. Just grab the waistline. And throw the waistline in. So the mean waistline is below 40. Okay. So we have the dummy variable. Dummy variable, you just put zeros. And since it's so easy to put multiple zeros, just drag the whole thing. So in this case, is it a one-tail test or two-tail test? To test whether the mean baseline is below 40, can you use a one sample t-test? Is it a one-tail test or two-tail test? One tail, because it's below 40, okay? So the null hypothesis remains the same. Okay. The mean waistline equals to 40 inches. The alternate hypothesis is then the mean waistline is below 40 inches. Okay, this you have to take note with one tail test. So if we calculate, if the mean waistline is 50 inches, you still cannot reject null hypothesis. It's only one-sided. Okay? So be very careful with it. It doesn't matter what. It's almost like saying this. Okay. Let's say if this is the waistline. So you have 40. Okay. You put it on a t-axis. Let's say you want it to be below 40. Okay, so below 40 will be opposite side. So it will be here. This part gives you the entire 0.05. Here, you find out what is the T critical value for here. Which means that if you put it on two axes, this is where you reject the null hypothesis. Okay. Here is you accept the null hypothesis. It doesn't mean what is the waistline above 40. If the waistline is 50, 60, you still cannot reject null hypothesis. Because you can only reject null hypothesis is way below 40. Okay. So let's just do this. Okay. Go back and use your unequal variance. And now you can highlight the data columns. The mean is 40. Now you need to click on the labels. Okay. Then after that, just click OK. Now you have to know this test very well. Okay, because in your online test or this, you need to use it. And you don't have time for it. So this is the result. Okay. Now the mean waist size is 37.9 inches. Okay. The hypothesized mean is 40. What is important is you know that the mean waist size is below 40. But is it at this position or is it at this position? In the shaded region or not in the shaded region? That's all you want to know. Make sense so far? Okay. Because if it is at position A, you accept null hypothesis. If at position B, you reject null hypothesis. So where is it? You can only decide by what is the T critical value. So let's look at here. Your T critical value for one tail is actually plus minus 1.64. Okay, so here, this is actually minus 1.64 here because it's 0. But the T statistic that you calculated is minus 7.25. So is it in the shaded region or not? Minus 7.25. Where do you put minus 7.25 in the t-axis? Yeah, you put it somewhere here, right? Maybe it's way here, minus 7.25. So it's actually in the shaded area, which means that you reject null hypothesis. Okay. Look at the p-value. The chance of the probability of null hypothesis being correct is how much? Okay, it's 1 in a million billion. No, 1 in a million. Okay. Therefore, you reject the null hypothesis and you accept the alternate hypothesis. Yes.
Loss again.
What loss? Which one?
My own bio data set here is completely different.
Completely different.
Yeah, you see 45.
45. Do you get the correct data?
Waste, right?
Yeah, waste.
The diabetes data set.
Yeah, correct. How come your waste is very different from mine?
Okay.
Some you recalculate. I think you put something wrongly already. So that's your answer. Okay. All right. So the next one that we are going to do is how do you do your Z test? Now Z test, in your lecture notes, already given to you that it is more of a theoretical test. That is the basis of t-test. But in reality, in practice, we never use Z test. Okay, because population variance is nearly impossible to know. And for most of biological data, our sample size is also small, less than 30. Okay. Now, in practice, not in exam, in practice, when you go for your major project and so on, in event that you can use Z test and you use T test, you are still correct. But in event that you cannot use T test, or in event that you cannot use Z test and you use Z test, you're wrong. So T test is like a universal thing. You can cover whether you right or wrong, you still can use it. Right? So Z test itself, Excel does have some functions on that. But let's look at the regular formula for using Z test. Okay. So let's look at your Z test. Let's do a Z test function. Okay, you open up this function box. Now, what you want is the data that goes onto the Z test. Okay. And this function will only give you the p-value. It gives you a p-value of one-tailed Z test. Okay. So let's say if we take the waist size and we want to do the Z test version of this. Our purpose is just a p-value, for example. Okay. So we can say that the p-value for Z test, just put Z dot test. The array, just highlight the data that you want. X is the value that you want to test. In this case, it's 40. Sigma, you don't have to provide. If you don't provide a sigma, it will calculate from the waist size itself. Okay. And it will give you the one tail p value. That gives you 1. So technically, in order to find the opposite, you take 1 minus this. So what it's trying to say is, if you put this on a Z test, okay, so let's look at our results here. So let's say this is your waist. Okay. Waistline. The average waistline here is 40. Just now, our t-test gives you 37.9. Right? So 37.9 will be Hello. Yep. So 37.9 maybe all the way here. 37.9 because it's average. Let's look at the T again. So at 37.9, this area, what is the equivalent T value? It is given here, minus 25.3. So this is 0, this is minus 7, 25, 3. Okay. If we do it on the Z-test version, the area is going to be quite different. So 25 is 1.1 times 10 to the power of minus 12. So this area here is 1.1 times 10 to the power of minus 12. If we do it on the Z-test graph, the area here, this is for the p-value for t-test, right? For t, but the area here for the Z table, it will be equals to 2.04 times 10 to the power of minus 13. Which is actually one whole magnitude lower than that, 10 times lower than that. Okay. But nevertheless, it is still less than 5%. This number is still much lower than 5%. Okay. So similarly, can you find out what is the Z-score if you do it properly? We did that last week already. You use your normal inverse function to find out the probability is this. The mean is 0. The standard deviation you calculate yourself. So standard deviation dot S, this is minus 41.65. So on the Z-score, this is minus 41.65. So it's much lower than that. That's what I'm trying to say. Okay, so this is a quick way, but can you do similar to what we did for your t-test? Actually, if you go to your data analysis tab, there is a Z-test to sample for means. All right. You can actually do that if you want to. How do you do this? It's exactly like how do you do your t-test. So you need a set of dummy variables, dummy numbers. So it's 0, 0, and so on. So don't bother with this. Take your data, go to your Z-test, to sample for means. It's the same thing here. Okay, range 1 and range 2. Your hypothesized mean will be, in this case, what is it? 40. Okay. Variable 1 variance, variable 2 variance, you don't have to bother with it. Let's see if we can calculate it. Sample mean variance. Okay. So the problem is the variance you actually need to have. Okay, you need to put the variance in. So how do you find the variance in the first place? Now the variance for sample 1, you have to calculate first. Okay. So the variance for waste, calculate the variance dot S for the waste. So you get the variance first. Okay. So the formula is just variance dot S. Or you can take standard deviation, square it. Once you have the variance. But can you find the variance for dummy? Do you think you can find the variance of dummy? No, right? Because everything is zero, so it doesn't move. So what you do is you go to the data analysis step. The variance for A, you just put the waste variance. Okay, so here you type it in yourself. It doesn't even allow you to do it. 0.98. The variance for 2, what is the variance for all the zeros? You just put a very small number, maybe 0.01. Okay. So this is an estimation. One person put 0.01, one person put 0.0001. It will give you a different answer already. Okay. So now this is the result. Your T statistic, your Z statistic, minus 7. And then your, so this is also minus 7.25. This is minus 7.25, quite close to it. And your p-value is 0.25 times 10 to the power of minus 13. Now, so essentially, we seldom use Z-test even in Excel. There's a lot more things for you to calculate before you can use Z-test. Okay. So assuming that you've done your tutorial already, why not you check some of your tutorial answers to see whether it's correct or not? How many of you have not done a tutorial? Okay, then go and do the tutorial lah. Okay. Yeah, so actually that's all for what we have today. You find that Excel actually doesn't cater for one hypothesis testing. Excel doesn't really cater for one hypothesis testing. You kind of have to trick Excel to do that. Okay, so basically, let me stop the recording for this.